Right, for this podcast, I've made a little scenario for you with Pepsi versus Coke to hopefully help you get a better grasp of the concepts behind significant, particularly type 1 and type 2 errors, and how they relate to the power of the test and to each other. Okay, go ahead and pause the podcast and read the scenario. Okay, as you can see, we've set up an experiment. We have a null hypothesis and an alternative hypothesis. How can we test our hypothesis? Well, it's a proportion, so we check the conditions for a 1 proportion z-test. Random, yes. Independent, yes. Certainly less than 10% of all the population. And because it's a proportion, we check the normality of our sampling distribution by NP and NQ. Part of the difficulty in grasping the concept of a significance test is because of what we don't know. We do not know the true population proportion. If we did, we wouldn't need to do a significant test. Okay, so what we're going to do is we're going to imagine two different realities. In one reality, there is no difference between Coke and Pepsi. The proportion that prefer Pepsi is 50%. And in an alternate universe, we're going to assume that Pepsi is the preferred choice, meaning that the proportion is greater than 50. Let's look at these two possibilities. In reality number one, there is no difference between Coke and Pepsi. So we would expect in a sample to get approximately 50-50, right? Well, let's just assume that this is true. When we use our significance tests, we could fail to reject the null hypothesis that there is no difference. In other words, assume that there is a difference, and that would, we could reject, fail to reject the null hypothesis that there is no difference, which would be what we'd expect. There would not be an error, right? That's when we're going to get close to 50-50. And there is no evidence to prove they're different. And we'd expect that because they aren't different in this reality. Or we could reject the null hypothesis and accept our alternative hypothesis that people prefer Pepsi. This, of course, would be an error because we know Coke and Pepsi are exactly the same. This is what we call a type 1 error, rejecting our null hypothesis when we should not. In this reality, in this specific reality, there is no chance of committing a type 2 error because that would require there to be a difference between Coke and Pepsi. Okay, so there's a type 1 error in this reality, but no possibility of a type 2. Now, put on your time travel suit or your space-time continuum suit because we're going to travel to an alternate reality. Imagine for a second that people do prefer Pepsi, and we know how far-fetched that is since Coke definitely tastes better. If this is true, then our significance test will either reject the null hypothesis and accept our alternative hypothesis that people prefer Pepsi. In other words, we reject that there is no difference and we accept that people do prefer Pepsi. And if that happened, there'd be no error at all. Of course, alternately, we could fail to reject our null hypothesis, in which there is no difference, and that would be a type 2 error because we should have rejected the null hypothesis. In other words, we're saying, you know what, there's no evidence that there is a difference, and we'd be wrong. There is a difference. So that would be a type 2 error. In this situation, it would not be possible to commit a type 1 error. Okay? In one reality, you cannot commit both errors. So how in the world do we know what is real? We don't, normally. That's why we talk in terms of probability, not certainty. In reality 1, we know our probability of committing a type 1 error is the same as our significance level. Why? Because we set our significance level to the probability low enough that we believe that could not be caused by mere chance. In reality, too, if we happen to know the true population proportion, remember reality 2 is where Pepsi is better, then we could calculate the probability of committing a type 2 error. And we call that the probability beta. But if we already know the true proportion, why would we need to know the probability of committing an error? Well, we often talk about the power of a test, which is the probability of rejecting the null hypothesis given that the alternative hypothesis is true. And this is the complement of beta. Power is the complement of beta. That's something you really, really need to know. So what else can we know? Well, when we use a significance test on a sample or proportion, we have to keep both realities in mind, and we decide which is most likely. Keep in mind, we don't know which universe we're in. We don't know what the true reality is. Are they the same, or is Pepsi better? We won't usually know at the time if we made an error. How can we know if we made an error if we don't know what the true proportion is? We will know what is most likely and where to put our money. Errors are often discovered later after additional samples or experiments.